Alright, now we will try and set the simulation up for dynamics. In dynamics you don't need the shortcut columns, so just delete them. Spreadsheet was there only to calculate the total revolver duty. We don't really need the spreadsheet either, so delete that too. Okay, now let's put in controllers. Let's put in the controller. So you see this control ops, click on that, ratio PID, profit controller, where's the PID controller, ratio controller, split range, MPSA, profit. Come on man, we don't have a simple PID controller. Come on. Hang on, कुछ तो गड़बड़ हुई है भाई. PID controller, it's right here. PID controller. So just put in the PID controller. This would be a flow controller. This would be column 1 pressure controller, column 1 level controller top, column 1 level controller bottom, column 2 pressure controller, column 2 level controller, column 2 level controller, and we'll also have at least 2 temperature controllers. Temperature controller number 1, temperature controller number 2, and maybe, just maybe, you want composition controllers, or shall we just do dual ended control? We'll see. Okay, so now this guy, select process variable, flow rate of stream number 2, and we'll just keep it molar flow. In practice it is actually volumetric or mass flow. Molar flow, where is M? Molar flow kahan gaya? Molar flow. Okay, so molar flow, in order to adjust the molar flow, output that's going to be adjusted is VLV 101 or VLV 100. VLV 100, where's VLV 100? Okay, actuator desired position, there we go. And just so that it looks good, transform mirror about X. Yeah, so this is a flow controller. It's still red, it's saying unknown ranges for the process variable. Well, so the process variable goes from 0 to twice the steady state, 200 kilomoles an hour, and we will say that it is, time is 0.5. If the flow increases above set point, output of the controller and hence the valve opening must decrease in order to bring the increasing flow back. So if process variable increases, decrease the valve position. This is called reverse action. So reverse action is fine. That's it. So go to the automatic mode. So this flow controller is on automatic. Okay. Then pressure control, tower 100, condenser, vessel pressure. Where's vessel pressure? Vessel pressure. Okay. And in order to control the vessel pressure, we must adjust Q106, the condenser duty. Select output is Q106. Okay. Control valve. Okay. Now it is saying the control valve is not sized. So let us size the control valve. So click on control valve. Base case duty is 2.7, 2.8. So I think base case is at around 50%. So minimum is 0, maximum is twice of base case. Twice of 2.8, double 5.6. 5.6 E6 kilojoules an hour. So that's your control valve size. Unknown ranges for the process variable. The column is process variable. So I don't know, 90 to maybe 130. Yeah, and should be pretty tight. So tau I would say about a minute, and the gain, crank up the gain. Gain should be maybe, I don't know, 3 or 4. This has gone to 0, break it 50%. And if the pressure is increasing, the cooling duty must also increase. So this is direct action. So direct acting, put it in auto mode. I think that's done. Okay, so this is just the pressure controller. Now we will level controller. So select process variable T100 condenser liquid percent level. Okay, and the output that we will adjust is VLV 101. Select output VLV 101, actuator desired position. Okay, parameters, level could be 0%, level could be 100%, and we will say okay, so if the level is increasing, open the distillate, increase the distillate. So that's direct action, and we will just say that the gain is 2, actuator gain is 2, make it automatic. I think that takes care of the level controller. Now over here you see the way the dynamic simulation would run, the controller would say give me 5% increase in cooling duty. HYSYS will immediately give 5% increase in cooling duty. In practice though, what will happen is cooling duty, HYSYS, the controller says give me more cooling duty, cooling water will increase, tubes will become colder, and then you will start getting more condensation. You see what I'm saying? So there is a dynamic lag between what the controller asks and what the duty should be, and that lag is not there in HYSYS. So to make the simulation realistic, we will say PV conditioning, process variable conditioning. No, signal processing. The output of the controller should be filtered, and the output time constant should be, I don't know, maybe 1 minute. Yeah. Okay. Select process variable T100 reboiler liquid percent level, vessel level, I don't know, liquid, I don't know, phase level, reflux percent, reflux downstream, tube, vessel liquid volume, vessel temperature. अबे यार कहाँ गया इसका? Vessel liquid volume percent, liquid percent level, हाँ level कर लो. Okay, and output that will be manipulated is VLV 102. Output is VLV 102. Okay, and as before, this is a direct acting controller. Process variable minimum maximum is 0 and 100. Gain of 2 looks fine to me and should be an automatic. Yeah, so this looks okay. These are level and flow controllers. We need to make sure that too much benzene does not leak down the bottoms. For that we will put in a temperature controller. Let's look at the column profile. So performance column profiles. बढ़िया चलाओ यार. Let's look at plots, view graph of the temperature. अरे यार ये क्या yellow? That's stupid graph. Okay, so if you look at this, seems like the place where the temperature is changing the sharpest. So 20, 21, 22, 23, 23, 24th tray. So let's just say we'll control the 24th tray temperature using the reboiler duty. Okay, so here we go. Select process variable T100, main tray section, stage pressure, stage temperature, sorry, stage temperature. अबे यार कहाँ गया? Stage vapor कहाँ गया यार? Stage temperature, which stage? We decided number 24. Okay, so stage 24 temperature will be adjusted by manipulating reboiler duty Q105. So output is going to be Q105. Q105 control valve. Okay, size the control valve 0 to what? 4.1, so 8.2, 8.3, so 8.25 E6. Yeah, so we are approximately at 50% at base case. So parameters, process variable minimum is, यार टेम्परेचर क्या है यार, जरा देखो जरा स्टेज 24 का टेम्परेचर कितना है, कॉलम प्रोफाइल्स. If I look at stage 24, 114, so I would say 90 to 150 maybe a decent range. Yeah, so 90 degrees Celsius process variable minimum, maximum is 150 degrees Celsius, and by default we will have the reboiler duty at 50%. If temperature is increasing, reduce the steam to the reboiler, or reduce the reboiler duty. So reverse action is okay. Make it automatic. Tuning, I think we will do tuning later on. Let's just make it, I don't know, 10 minutes and maybe 2. Okay. Alright, so ऑटो ट्यूनर कैसा है इनका? बेकार है यार इनका ऑटो ट्यूनर. ठीक है, जाने दो, कोई बात नहीं. Also, as before, what we will do is parameters signal conditioning processing. So the output of the controller will have maybe a 1 minute lag. I suppose we can also put a, because temperature sensors are take time to respond, so maybe a 30-second first order lag there too. Okay, just to make the simulation a bit realistic. Alright, so controllers on the first column have been set up. How will I manage the reflux? One is to keep the reflux in ratio with the okay, so what we will do, just for the sake of demonstration here, you could have a temperature controller adjusting the reflux ratio, but then that will be two temperature controllers on a single column. They can end up fighting each other. So what I think we will do is, the operator will set the reflux ratio to whatever he or she wants it, depending on what's the purity of the distillate. Yeah, I think that's what we'll do on the that's how we'll manage the reflux. Okay, so now let's pressure controller for T101, condenser, vessel pressure. Okay, this vessel pressure is adjusted by or maintained by adjusting Q108. Select output Q108 control valve. Okay, it'll say what's the size of the control valve. It'll say okay, it's 0 to 7.15 E6, and by default you are at 50% opening at base case. प्रेशर कंट्रोलर है तो गेन थोड़ा ज़्यादा कर दो, टाइम कम रखो. Again from 90 to maybe 130 kilopascals, and this should be about 50. It should be a direct acting controller, automatic. Yeah, so that's the pressure controller. T101 condenser, liquid volume percent, liquid percent level. Okay, parameters. It should be 2. It should be direct acting. Process variable level is 0 to 100%. Automatic. Similarly, over here, process variable is T101 reboiler liquid volume percent. कहाँ गया यार liquid reboiler vessel liquid percent level. Okay, ranges are 0 to 100%. 0 to 100%. Should be a direct acting controller with a gain P only controller is fine. Make it automatic. We also need a temp. अच्छा output हमने डाला ही नहीं. Okay, so output should be VLV 104. Actuator desired position. Okay. Okay, so that's finally the temperature controller. Select process variable. Acha, now we need to figure out what is a good tray temperature to control. So let's look at the temperature profile, performance, plots, view graph. यार ये येलो कलर मुझे बिल्कुल बकवास लगता है. Okay, anyway, let's look at the graph, and to me it appears somewhere here is where the temperature profile is the sharpest, so maybe 32 or 33, tray number 32 or 33, so we will do that. So this temperature controller will maintain tray 33 temperature. So stage temperature, which tray? 33, tray 33 temperature by manipulating Q107. Select output Q107. कहाँ गया यार Q? Q107 control valve. Okay, the control valve, let's look at the control valve. It goes from 0 to 3.54, so that's actually 7.1 E6. E6, and we will say that the reboiler duty is what? 50%. So go to the parameters tab, temperature of the tray, column profiles, 33rd tray temperature is 142.6, so I guess 125 to or 120 to 160 sounds good to me. Okay, so 120 to 170 maybe. Yeah, that sounds good to me. So the process variable is 120, minimum is 120, maximum is 170. If the temperature is increasing, reduce the steam, so that's reverse action. Make it automatic, and we'll just say gain is 2, and this is about 10 minutes. And manual में जाके इसको 50% पहले कर दो, and then you convert to automatic. Okay, this is what we have. We also need to maintain the reflux in ratio with the feed. Number 1, so L by F, column 1. Okay, spreadsheet, column 1 feed, L by F, column 1 feed, L by F desired. Okay, so column 1 feed, import variable 3 molar flow rate. Feed number 3 molar flow rate. कहाँ है यार, कहाँ है भाई, साला कहाँ गया यार, molar flow. Okay, L by F desired, इस वक्त L कितना है? Column, go to the monitor page, update inactive. Reflux rate is 58.35. So about 0.5835. Okay, so desired ratio is 0.5835. So therefore L desired is going to be equal to B1 star B2. B1 star B2. Okay, this is what we want, we will be writing. Alright. Similarly here, column 2 feed rate. Import करो, इसकी value is import. So sorry. Import variable, the feed rate is going to be number 9. So number 9 molar flow. Number 9 molar flow. Okay. This is column 2 feed rate. L by F desired, as an operator I can change its value. So L feed rate is कितना है यार? Molar flow is 66.64. 66.64. This is the feed, and the reflux rate that we have on this column. So go to design, monitor, update inactive. Reflux rate is 74.47. So 74.47. So the ratio is actually just calculated 74.47 divided by 66.64, slightly up 1.1, maybe 1.1175. Okay, 1.1175. Alright, so the ratio desired here is 1.1175, 1.1175, and therefore L desired is actually B1 star B2, sorry, is equal to B1 star B2. वो उसने value calculate कर ली. This value we will import in dynamics. Right now we'll keep it fixed. Okay. So we have put in all the controllers. Let's just check. They are all in automatic. Flow controller should be reverse acting. Tuning looks okay. Pressure controller should be direct acting. Tuning looks okay. Level controller should be direct. Looks okay. Level level controller should be direct. Looks okay. Temperature controller should be reverse. Automatic. सब ठीक ही लग रहा है. Pressure controller should be direct. Looks okay. Level controller should be direct. Looks okay. Level controller should be direct, automatic. Looks okay. टेम्परेचर कंट्रोलर, अच्छा बाय द वे पीवी कंडीशनिंग यहाँ पे करी क्या? सिग्नल प्रोसेसिंग, हाँ यहाँ पे नहीं करी. तो प्रोसेस वेरिएबल नहीं, आउटपुट पे फिल्टर एक्टिव करो, एंड दिस शुड बी अबाउट 60 सेकेंड्स. प्रोसेस वेरिएबल पे भी फिल्टर एक्टिव करो, दिस शुड बी अबाउट 30 सेकेंड्स. ओके, यहाँ पे किया क्या? सिग्नल प्रोसेसिंग नहीं किया. आउटपुट पे करो यार, इस पे अबाउट 60 सेकेंड्स. ओके, इट लुक्स ओके टू मी. Automatic, reverse acting, yeah, so everything looks, this looks like a reasonable first pass for the controllers. Now what we need to do is size the valves. So go to the dynamics tab, size the valve, and then it will calculate its conductance. Size all valves. Go to the dynamics tab, size valve, dynamics tab, size valve, dynamics tab, size valve, dynamics tab, size valve. So the sizing of this valve fixes its resistance, and as the opening is changed, the resistance changes, hence the pressure drop changes, and hence the flow changes. Okay, we also need to size the reflux drum, reboiler duty, reboiler on both the columns, as well as the diameter of the two columns, because the diameter sets the hold up on the trays. So okay, so in order to do that, go to the column environment. Let's look at, I just do it this way typically. If you go to the properties tab of the boil up stream, go to the properties tab of the boil up stream, and you see that the वॉल्यूमेट्रिक फ्लो कहाँ गया यार, लिक्विड नहीं, लिक्विड नहीं यार, मोलर फ्लो, मास फ्लो, अबे यार ये बॉयल अप का और नीचे कुछ है कि नहीं है, प्रॉपर्टीज, हाँ सॉरी, एक्चुअल वॉल्यूमेट्रिक फ्लो इज 2771 मीटर क्यूब पर आवर, and what we want is, that is 2771 divided by 3600 meter cubes per second, and what we want is 0.8 times, because 20% of the area is occupied by the downcomer, so the way only 80% of the cross sectional area is available for the vapor to flow. So 0.8 times pi d square divided by 4 times the vapor superficial velocity should be equal to 2771 divided by 3600, and we will take the vapor superficial velocity to be about 0.7 meters per second, and this gives an equation between one equation in D. So it turns out that D is equal to 2771 divided by 3600 divided by 0.7 meters per second times 4 by pi divided by 0.8 square root of all this. So let's do the calculation. Can we do it in Calc? Let's see, I don't know, square root है क्या, हाँ चलो है तो सही यार. So 2771 divided by 3600 divided by 0.7 divided by 0.8 divided by 3.142 star 4, इसका आंसर आया इतना, इसका स्क्वायर रूट निकाल लो 1.32. 1.32, okay, by, so the diameter of the column should be about 1.3, 1.4. Let's look for how it is. So rating, diameter by default is 1.5, make it 1.4 maybe, looks okay to me. Now what should be the volume of the condenser? Well, the reflux flow rate is 5.644, the distillate flow rate is 3.2, 5.66 and 3.2, 5.6 and 3.2, yeah, 3.3, so 5.7 and 3 is 10, 5, 9. So total flow rate of the liquid through the condenser is 9 meter cube per hour. So if I make the tank volume 9 and the tank is fully full, then the residence time is 1 hour, 9 meter cube. But if the tank is only half full, residence time is 30 minutes. Rule of thumb is the residence time should be 5 minutes, so 1/6 of 9, so 9 by 6, how much is that? 1.5. So the volume of the reflux drum should be about 1.5 meter cube. So go to dynamics, volume is 2 meter cube, yeah, that's fine, but if you want, insist, we can make it 1.5 meter cube, that's fine. We go down, the liquid going into the reboiler is, volumetric flow is 24, so 24 divided by 6 is about 4 meter cube. So 24 by 4 is 4 meter cube. So the reboiler, go to the dynamics tab, its volume should be 4 meter cube. Alright, so the reboiler has been sized. We also need to have the resistance of each stage to vapor flow, and this steady state delta P method. So we have calculated the resistance of each of the trays to flow. Okay, so with this I think we have done all the necessary sizing on column 1. So get out into the main simulation flow sheet, and now we need to do the same thing for column 2. So go to the column environment. Let's look at the vapor rate here. Boil up properties क्या हैं भैया इसके. Actual volumetric flow 2396. So what we need to do, 2396 and 2771 about the same, no? So 2396 divided by 2771 square root of this. Okay, so calci 2396 divided by 2771, this is what it is. Square root of this is this much, and our diameter there was 1.32 star 1.32 1.22. So maybe we'll just make it 1.3 meter. The diameter will make 1.3 meters. Rating diameter is 1.3 meters. Okay. Then we also do the calculate K values for all stages, and then we need to size the drum. So property is kitna bhai, 8.8 is the reflux, and distillate is about the same, properties. Actual volume flow is 3.945. अबे यार ऐसे कैसे हो गया 4.